Hello community, so great you're back. Let's see if we can build a unified theory of agentic RAG system with LLM reasoning. Now we're almost there. You remember in one of my last videos we talked about self-learning AI agent with the reasoning power. We had a look at the RAG3 system in reinforcement learning, and then we looked at hypergraph reasoning with reinforcement learning, the graph R1. And we found that it is not just anymore about building smarter agents or multiple agents. It is about designing a complete symbiotic system where the agent and its knowledge environment co-evolve together. And you saw this very beautifully in this video here where we talked about UR2, the unifying the RAG complexity and the reasoning complexity of AI systems through a complete new reinforcement learning cycle. So we want to have here the retrieval and the reasoning combined here with a new learning process. And of course, we go with the reinforcement learning process. Now remember in the graph R1 framework, we had a new agentic RAG paradigm. And of course, we used here the simplest GRPO. And it performed a multi-turn traversal on the knowledge hypergraph itself. But you know, a hypergraph is just an object we can build and deconstruct. So what do you think about we do something new today? We have a new paper. So we go for a domain-specific multi-tool action space. So we go now here, we depart here from a graph R1, and our new agent is not just learning here the search functionality on a hypergraph, like a single tool use, but it is learning to be here a very special new agent, let's say in medicine, with a diverse toolkit. So we go here from one tool, let's go to 5 tools. So what we are witnessing now, and there are a lot of other papers I had not the chance to present to you, but I have a feeling that there is a kind of a convergence all around the research teams on this planet towards kind of a unified theory of agentic RAG system that have to integrate here the dynamic representation of the environment itself. Because think about it, if it's a hypergraph or we build here a math database structure in any new mathematical space, it is not really the complexity. The complexity that we have to solve is here the co-evolvement of agent and environmental data and knowledge representation at the same time. So I have a new paper. Deep-DxSearch here is a new specialization, a new addition to this discussion here. And we take now here the whole system and we put it in a real world environment. We say enough with theory. We want to have now the performance data of an operational system for medicine, from a hospital, from a medical diagnosis. We want to see the performance jump. Is it there or not? Is it real or is it just a hype? So here we have the study of today, August 21st, 2025, from Shanghai Jiaotong University and the Xinhua Hospital affiliated with the university, the School of Medicine. Beautiful, thank you to all the authors. And we are talking now about an end-to-end agentic RAG system that has been trained for diagnostic reasoning. So an AI system that utilizes here everything what we know, the latest, if you want, state-of-the-art knowledge, the leading and bleeding edge of AI research. And we put it all here into one brand new system. And they tell us, you know, we have to do this because our current diagnosis AI, we have inherent knowledge limitation. We still have massive hallucinations. We tried here with RAG and with tool augmented agentic methods, MCP protocol and whatever. But they tell us, hey, you know, there remain key limitation to the system. So we have to do something brand new. So they define now a new agent, an AI agent with an LLM at its core, to perform 5 distinct actions. This is what is really needed here in a real hospital and a real doctor diagnostic process. Reasoning, lookup, match, search, and the final diagnose. So what is it? Reasoning, you are familiar. This is the internal thought process of an LLM. This is the parametric knowledge that you see here in the thinking tokens. This is not associated with any external tool call. Lookup, hey, let's have a look at the database of the medical database, of medical textbook, whatever. Match, Now we have a real-world patient record database, and now we have a real-world search here for similar clinical cases. Search, generate here some medical knowledge corpus. Let's, I don't know, read the latest 1000 medical research paper on this particular topic that you're interested in. And then in the end, you combine everything and you come up here with a final diagnosis, the final answer. Now, it is currently independent how you take this action. You can have a call to an MCP, the Model Context Protocol Server, Client-Server Architecture. You might go with Retrieval API under the hood. It's not really important. We just want to have here a basic understanding here how we have to modify the learning process. Because going from 1 to 5 is quite complicated, but we can manage this. So this new agentic system, the new agent here does not have arbitrary tool access. We have a constrained tool access. We want to have a learnable action space that we as humans can still understand. Therefore, we limit ourselves to 5 actions. It is really deliberate. It kind of stabilizes here the reinforcement learning, the training process itself, and makes it much more analyzable for us humans to understand what happened. So the innovation is here not just hooking up more tools, and some of my viewers said they have 27 tools operational. We don't want to achieve this. We want to go baby steps, 1 tool, 5 tools. So training now a single new agent with the reinforcement learning methodology. I will show you what is special about this particular reinforcement learning to decide not only when that we have now, but also how to use here a very fixed tool set. And let's say we have an MCP client-server architecture. Great. Why we have to do this? Because there's only one reason. The inference-only agentic RAG system fails in the real-world system. It might be great if you have an academic performance test, that is known for years and is publicly available. But what happens if you're really in the hospital? Now, you might ask, but why does it fail? Eh? Now, an inference-only agentic RAG means, and let's have a look at the details, that the LLM gets rules, like first search here the PubMed database, then try a summarization, and then come up with the diagnosis. Because you have provided different templates, different complexity templates. Yes, I know, but they are even chained templates. But those rules are handcrafted by humans or other AI systems. They are static and they are non-adaptive. And even if you have a for or an if-then loop there, it's not adaptive. The LLM never learns when to search, how to formulate here the particular queries, or even have a clear stop criterion. Yes, you can hard code it, but this might just be a waste of resources. And we found, the authors of the paper found here in the hospital, the failures appear here in medicine because the evidence is long-tailed, we have a lot of noisy data, and sometimes here the information can be misleading that we get back from our RAG system. So the complete data knowledge pipeline is brittle and unadaptive if we have inference-only agentic RAG system. So we have to improve. So what is the solution? And the authors of the new paper said, hey, easy, ne? We train the new agent as a policy in itself, understanding here the deeper operational methodologies of the reinforcement learning process. So this new research paper reframes now the process of reinforcement learning, the flow itself differently. Let's have a look at this. Now at first they treat here the LLM as a policy in itself, given here a reinforcement learning environment. Now of course we have a data and knowledge environment within, so this means we have a retrieval universe with guidelines, all the private patient records, all the public medical databases, everything on Wikipedia, everything on medical textbook, everything that is available on the internet. And then we have to have a very strict policy, because now the artificial intelligence has to choose here a very particular action during each time step, based on the current state, on the previous reasoning and the retrieved documentation, and now it has to go baby steps in its data and knowledge aggregation. Maybe it decides it needs additional data, maybe the data are not available in the format that it needs, you understand it. But the most single important element here is the reward structure, the reward function. And the authors had invested a lot of effort to define a complete, absolutely fascinating reward function. It is structured in a way so that this new agent must not only find the correct format, let's say JSON or whatever you decide, then retrieve the relevant evidence from maybe non-structured data representation, plus have a coherent reasoning process to arrive at a final diagnosis in a correct, detailed, and accurate way. No, it is even much more complex. Let's have a look at the reward. So we have a 5-action agent. Remember, reason, lookup, match, search, and diagnose. And this is trained, and we go here with the simplest, with a group relative policy optimization, GRPO. And then they decided they go here with a specific reward function. They go for engineered software rewards for the strict format compliance, the retrieval quality, the analytical organization, and the final diagnostic accuracy of the diagnostic system. If you want to have it a little bit more in detail, we have here from the reward design itself, so the engine of the learned behavior that we want, that this is what the system learns. Hard 0-1 coefficient, structural rules are violated, you get it here, enforces an exact workflow structure before any content is judged. If you want, this is here a format gate, because if the workflow structure is not met, this is the end. Never mind what is the exact content. Then they looked at the retrieval quality. For example, patient matching reward encourages here retrieving similar cases that share here the ground truth diagnosis. Hopefully that all the patient and the diagnosis in the database are really the golden truth. Then you have analytical organization. This means the rewards here, coherent stepwise reasoning that integrates here the evidence. And it, if you want, has penalizes here the meandering chains, just wandering around. The AI is just looking around. No way. And finally, the accuracy of the diagnosis itself. So the final label correctness contributes only after the format, the retrieval, and the analysis checks out, pushing here the policy to earn the accuracy via the good process and no shortcuts at all. So you have the complete reasoning chain established. Now, of course, you need to have access to the domain-specific environment. And in medicine, guess what? So the environment from the agent can learn about 257,000 disease phenotype pairs and multi-source verification. So everything that you have available in the hospital, plus patient records. These are your golden truth test cases, no? 177,000 curated cases, long-tailed, 14 body systems revealing everything that you need, robust retrieval, critical elements, and finally the theoretical body of medicine. No? 24 million PubMed articles and textbooks and Wikipedia and Summarizer and whatever you have. But you see, if you are now a little agent and you say, my goodness, what I do here with this mountain of data, how can I perform now an intelligent structured search of all of this? So what is the new idea? You don't prompt here an LLM to use tools. This is what we do today, no? Or you have a template. Hey, this template describes here exactly how to use or an MCP client-server architecture, or you just go with a classical API call or whatever. No. We have an LLM, and this is an intelligence. So why the heck not use the intelligence of the LLM itself? And listen, this is just another pattern that the LLM learns. Tool use is a pattern. So therefore we say, wait, we don't do here everything for the LLM. Let's do some training for the LLM. And we use here train a policy to decide which tool to use, when to use it, and why to use this particular tool from a given tool set, given here feedback from the real environment. So I like this approach here from the authors of this new paper, because this is exactly what we should do. Use the intelligence of the LLM. Don't have, I don't know how many people trying to code or prompt engineer or context engineer or whatever. Come on. We have an intelligence in the eye. Let's use it. But of course, you have to provide here a retrieval environment that actually reflects here the practice that you want to have, the ground truth you have to make available. You have to have your hospital guidelines, your medical guidelines. You have to have your cases. You have to have your biomedical complete literature in your domain experience here. With capacity, you have maybe access to other LLM to summarize here real complex long returns. You have to find a representation of the data that is optimal for our new agent. Plus, you have to define the efficient reward structure for the real-world case that force the structure and the reward and the good retrieval of anything for the analysis because you want to have the best accuracy. Therefore, the new agent learns here traceable workflows and not just labels or templates. You see, the new reinforcement learning agent is not just learning when to retrieve, but what kind of retrieval is most appropriate at each stage of the reasoning, at each time step, for each complexity level. It is like another language that the LLM is learning. So, no problem. It's just a new learning pattern. It's a very specific pattern, no? Because the LLM must learn the strategic difference, as I showed you, between just looking up here a textbook definition to find a solution, or find a similar patient case to understand, hey, 3 months ago there was a patient that had the exact same symptoms and exact same conditions and everything fit, so I have now maybe a starting point for my diagnosis as an AI system. Or you search if you are absolutely stuck in as an AI for the latest research paper. You see, it is only pattern, and an AI is a perfect pattern matching machine. Plus, we have a little bit more complex policy, a more nuanced policy here than, as I showed you here in search R1 or in graph R1, than simply a binary search or don't search decision here, either on hypergraph or databases or whatsoever. So you said, what are the results? What have they achieved in this real world scenario? In the hospital, what happened? Now, if you look in distribution data, it is interesting. So for common diseases, and don't ask me what they classify as a common disease, it's meta-dialog dataset here, this new system here, and they used here a Q1 2.5 14 billion model, of course, because they have to do a lot of optimization. But just to show you, a tiny little 14 billion model improves the accuracy by 24 percentage point over the normal RAG baseline. So they went from 24.6 to 48.8. For a 14B model in a medical diagnosis system, this is, still below 50%, but this is another topic. But there was an improvement. And I think today we're all about baby steps, improvements. Now, for the rare diseases, it's even better. They achieved here 35.7 percentage point over the training-free RAG system with a retrieval. So they went from 34 to 70%. 70%, yeah, we can start to talk that maybe this might be helpful. So I think this is the right track. Yeah, if you go here with the classical open source system like a DeepSeek R1, you see that this 14 billion here outperforms here a 671 billion R1 system, nearly 20 percentage points. And if you go here for the rare diseases, you see by nearly 30 percentage points. And if you want to have the real percentage, it's an improvement of over 150% if you go with the Deep-DxSearch algorithm that we just talked about in this video, compared to here a simple DeepSeek R1. Here you have, if you want, a complete process here, A, B, C, D. And yeah, let's zoom in here on the performance data. Here you have it. Now on the top, you have the common disease diagnosis, and on the bottom, you have the rare disease diagnosis. Anyway, on the y-axis, you have the percentage of the accuracy achieved, and on the x-axis, you have 3 areas. You have the base LLM, and you have here the Q114B, the GPT-4 Omni, then the Q140B with a retrieval, a RAG retrieval, and a GPT-4 with a RAG retrieval. Then you have dedicated medical systems like MedRec, MedGamma, multi-agent conversation for medical. And then, of course, the latest here segment here is this new system we just talked about, either implemented on a Q1 7B or on a Q1 14B. So what you see, beautiful. This is a little bit strange in the presentation because you have to read it in the following way. We compare now the Q1 14B, so this point, with 14B with reg retrieval. So you see, we improve our accuracy from a vanilla Q1 14B from 20% with the classical reg to, let's say, 30%. So this is it. Or we go with GPT-4 Omni to the GPT-4 Omni retrieval, I think less than 10 percentage point improvement. So you have to read it in this particular way. But in any way, if you go here with the top 1 accuracy or a top 5 accuracy, you see this really shows us there is an improvement in the medical domain that we're testing the system. And even if you go with other dedicated medical reg system, like this one here. So, okay, it seems to work. Let's go on. So here you have it now for 3 other LLMs, the Q1 2.57 base, the Q1 2.5 14 base that we just saw, and they even tested out a Llama 3.18 base. And here you have now for the common disease and for the rare disease, here you have all the data available for you. Now, if we go out of distribution, the evaluation for the out of distribution data, for this agentic reinforcement learning training here, we see, I think, the following. Just look here at the 14B base model. Now, I think this is, we should not go any smaller. The vanilla Q1 2.5 14B here for a particular diagnosed system accuracy at 5, we achieve 34.6%. With the classical retrieval reg system, we have a decline in the performance to 34.0%. But luckily, this new method we just discussed in this video brings us up to 42.7%. Now, I would say, is 42% acceptable for medical diagnosis? I personally would argue, no, not yet. We are making some progress. You see, classical reg systems are not really there for where you would argue, hey, wow, what an improvement. But to go from 34 to 42, yes, we are heading in the right direction, but there's a lot of work in front of us. Maybe we have to invest a little bit more money. I mean, some university on this planet has to invest much more money. Not a 14B, let's go with a 70B, let's go with a 150B model. We need to have the reasoning power here if we go with the classical models. So we have to pay. But I also showed you that some LLMs are much better as MCP agent. If we would go with an MCP client-server architecture, you know, really interesting would be if somebody would be able to pay for the GPT-5 optimization for this new methodology for the medical sector. But who would invest this money? If you want to see here the statistics on the training and the evaluation data set, and if you're interested in medical and you want to see here absolutely here the details, there's a ton of additional data for you waiting here in the original publication. Please have a look at the original paper. Of course, if you're just interested in the code implementation, we do have a GitHub. You have everything for the direct usage here. You have how to prepare your data. If you have other data sets, if you have your clinical training data sets, your medical data sets, they provide here real nice. And yeah, this is the GitHub that they refer to. Unfortunately, just 13 stars. I think that's a pity. It's such a beautiful idea. Have a look at this. So I think in total, we can summarize this. Graph R1 in the last videos, I think it proved that the structural representation is key to the precision of the new AI systems. You remember Graph R1 also modified here the data representation itself of the external data to optimize its own accuracy. And today's new research paper with Deep-DxSearch, I think also proves that a functional multi-tool action space is key here for some complex real-world workflows here in the medical domain. So, of course, we limited ourselves to 5 actions, but never mind. If in your medical domain or whatever domain you have, you need 12 specific actions, or those are the dominant one, then you define them. You can define now the optimal data and knowledge representation for those domain to have here really the perfect real-world workflow, and you can let your system train on real-world data. Don't restrict yourself to fixed template. Don't restrict yourself to some stop criterion that you hard code. Don't limit yourself to a reasoning loop of 3 or 5, as I can see in a lot of programs. Let the AI, the large language model, do the learning. This is the pattern matching machine. This is here just another language, just another complexity for the future AI systems to learn. We as humans, we don't have to hard code anything. We just have to build better AI LLMs. I think this is here the message, and we have not just to build better agents, where the core of the agent is the LLM. We have to design better systems, some symbiotic systems where we have a representation of the external data that can be transformed into a data and knowledge representation that is optimal for our specific agentic multi-agent structure. So therefore, I hope I've provided you a glimpse, maybe just an idea or a feeling that there could be a unified theory waiting for us, that finally our agentic RAG 3.0 systems come together, combine really the LLM reasoning process that still fails in the static forms of RAG, and we can use here what we know about teaching an AI to learn. We can optimize our reinforcement learning process, go with a simple GRPO, go with the most advanced system that you want, but you have to be careful defining here the reward functions, and then I think we will see that all those systems come closer and closer together, and then it would be really fascinating if you want to do research, if you want to contribute to the AI of the future. This is a system that is waiting for you, that is waiting for your contribution. So I hope I've given you some idea how fascinating it could be if you're interested to work in AI or work with AI systems. What are the challenges right in front of us? And if you want to participate, hey, why not subscribe? And I see you in my next video.